Okay, we have here an integral inside of a limit. This was from Berkeley Math Tournament 2024, calculus number 5. We have the limit as n's approaching infinity of the integral from 0 to n, x times the floor function of x over n cubed dx. Okay, so at first it's kind of intimidating having both an integral and a limit, and also we have the floor function in it. Now you may be thinking with n approaching infinity, so the denominator is going to infinity, so maybe it's 0. But then you think about the integral going to infinity, maybe it doesn't converge. So maybe it's going to infinity. And you might want to think of it like an indeterminate form, but I think we don't really want to deal with any of that right now, because you'll notice this n cubed, this is just a constant with respect to x. So I could actually just bring this up front and have it as 1 over n cubed. And what that's going to allow me to do is just kind of deal with the integral the way we would normally do it, and we can deal with the limit later. So now what I want to do is we'll just focus on this integral here, and the thing I want to deal with first is this floor function. Now the floor function is going to always round us down to the next highest integer value, and so what we can do to simplify this, if we break up this integral into parts that are separated by integer values, like if I start at 0 and our first integral goes from 0 to 1, then we're going to have this x, the floor in this region between 0 and 1 where this is going to round us down, it's going to round everything down to 0. So this first integral is just going away, and we don't have to worry about that. So then the second piece, if we're starting at 1, let's go from 1 to 2. Same kind of things happening. Between 1 and 2, the floor rounds us down to 1. And we could just kind of keep going like this, on and on to infinity, where it's always going to round us down to this lower bound right here. So what I want to do with this, rather than writing out a million terms, or an infinite number of terms, is let's turn it into a sum from 1 to infinity. And actually, let's not use n because we're already using n, and I don't want to confuse that. So instead, let's call this a k. So this thing is going to be the sum from k equals 1 to infinity, and then we're going to have all these integrals, and each of them are going to start at k and go to k plus 1. And then this value here is going to be the k value as well, but it's going to be a constant with respect to the integral. So let's just bring it out front of the integral, still within the sum, and then we're just integrating x dx. But of course, we can just go ahead and do this integral just using power rule on it. We still have this constant out front. So when we integrate this, it's just going to be x squared over 2 evaluated from k to k plus 1. Now maybe let's take this 2 right here and just bring it out front of the sum just so it doesn't need to bother us right now. So I can write it as a 1/2. And now we can just go ahead and evaluate at these limits. So we're going to have half times the sum of k, and then all this stuff, and then just plugging in these bounds, it's going to be k plus 1 squared minus k squared. Well, for this, I can simplify this just by multiplying everything out, expand this out to x squared plus 2k plus 1 minus k squared, and this stuff's going to cancel, and we're just going to have 2k plus 1 for all this. So next, let me just take this k and distribute it into the 2k plus 1. So now inside of our sum, it's going to become 2k squared plus k. But then let's just split this up now into two sums. So first the 2 and the half are going to cancel, and so our first sum is going to be just k squared. And then for the second one, we'll have this 1/2 in front on this k value. And so now that we've got this thing pretty simplified, let me clean up the board and see if we can do anything else to get this simplified before we put it back in the limit. Okay, now from here, the thing we notice about both these sums is they clearly diverge, right? Both of them, I mean, even just checking the ends, it's going to be going to infinity. Now, one thing that I did here that's kind of a mistake is I didn't mean to write this as an infinity. What I should really do here, because the upper bound on our integral is n, so I really should call this n, even though in the end we know it's going to be infinity. But right now we're not dealing with the convergence of this. We're not worried about any of that. So let's just write it as an n. But now doing it that way, we've got a formula for the first n squares and the first n natural numbers, and we can use that here. So for the first n squares, the formula is n times n plus 1 times 2n plus 1 over 6. And for the second one, we still got the half out front, but the formula for the first n counting numbers, this is going to be n times n plus 1 over 2. Then let's clean this up a little bit. I can put the half and the half together and write this as a 4. And maybe factor a little bit more. We've got n times n plus 1 here in common. I can factor that out and write it like this. And in order to deal with denominators, let's factor out a 1/12 just to clean it up, just to clean all the fractions out of it. So what's going to happen is this here is going to become just 2 times 2n plus 1. And the second one is just going to become a plus 3 with the 12 there like that. And now at this point, let's take this and let's plug it back into our limit and kind of simplify as we go. Now, first of all, we have a 12 here in the denominator, just a constant. So I'm going to bring that out front of the limit. So I'll have 1/12 here, limit as n's approaching infinity. Then we're going to have this 1 over n cubed from right here. And then here, let's bring this into the numerator right here. So we'll have n times n plus 1. All this, but let's distribute it out to simplify it more. So this is going to become 4n plus 2 plus 3 plus 5. But now I can cancel an n with one of these. And so this will become a 2 right here. I'll get rid of all this stuff that we don't need. And then let's distribute this all out and simplify. So we're going to have 1 over 12 times our limit. Then this is going to all be over n squared. Distributing this out, we're going to have 4n squared plus 4n plus 5 times n plus 5 times 1 is just a 5. But now all that we've got left is an easy limit to do. You can kind of just eyeball it. All you need to worry about is the terms with the highest power, the n squareds. Or, another way, if you want to do it a little more carefully, you could multiply n like 1 over n squared, numerator and denominator. Just doing that, when you multiply in here, these terms, all these lower power terms are going to 0. This is going to cancel with this. This is going to cancel with this. And so for our limit part, we just get 4. And so putting it together, dividing 4 by 12, we get our final solution of just 1 over 3. Okay, there you go. Really good one today from Berkeley Math Tournament 2024. Thanks everyone for watching. Have a good day.